Hey, what's going on, guys? Coming here. In this video we're going to learn about unit testing in x86 assembly language. But just to give you a little bit of an idea of how I personally feel about unit testing, I just say that I've rejected a countless number of freelance jobs forcing me to write some unit tests for the corresponding business operations related to those projects. And I hated that so much with all my heart that they couldn't really force me, and no matter what the reward was potentially for those kind of projects, still I couldn't really agree on doing that because I didn't see an objective why to do that. And who could have ever thought that one day I would encounter a project where unit testing is a must-have thing to be involved within the project. And this day has come, literally this day has come today basically. So just a few words about the project I'm currently working on. So I'm writing a 6502 processor simulator in x86 assembly language, and this is the bootable simulator. So the idea is that I just want to write this program, so it's like an operating system. You might think of this like as if it was an operating system. So you just write this operating system to USB flash drive, boot from that, and then you would be able to input the 6502 processor's machine codes. That's going to be an input, and as an output you will have those instructions being executed within the virtual CPU environment that I'm building. So it's all about executing this, it's all about interpreting the specific machine codes, like opcode with a following value, and change the internal CPU state based on that opcode and based on the data. So things like loading the value into the register in different addressing modes, setting the value from the register to the memory, transferring values between registers, and so on and so on. So all the 56 instructions that are available in 6502 processor by MOS company, distributed back in in Apple I. It appeared to be in 1976. I'm not sure whether this processor was whether the very initial version was released earlier than that date. I'm not sure, but anyway, it's very rare. It's kind of like almost 40 years, right? So it's really rare thing, but it's incredibly simple, minimalist, and I really love this processor. So I decided to emulate this, or better to say, just to simulate this. Okay, so before we start diving into the code that I have here, and before I start the demonstration and explaining through this test cases and how am I managing these test cases, I would like to share this Wikipedia article, again, like that I've been hating with all my heart when I was forced to do this and when I've been rejecting this sort of things. But anyway, now it starts making a really different sense to me as opposed to how this was back in the day when I was freelancing. And yeah, unit testing is not tied to any programming languages, so it's a concept. It's rather a development it's more like a development concept rather than something that is tied up to a certain language. Well, let's say in Python we have special classes like for unit testing, but it doesn't really mean that we need to use the object-oriented code to do that. So I just really want to give you a clear understanding of what the unit tests are and what are the exact cases when we need to use those tests, regardless of programming language at all. And then I'll try to show how this can be applied to this particular project that I'm currently working on. Again, like regardless of programming language. And then in regards to programming language, we'll see how the certain test cases can be implemented using the x86 assembly language, and how in particular this is going to be working in the environment I'm developing. Okay, so I really love this Wikipedia article on unit testing. So in computer programming, unit testing is a software testing method by which individual units of source code sets one or more computer program modules together with associated control data. Usage procedures and operating procedures are tested so to determine whether they are fit for use. So if we say this in simple words, so we have a piece of code, they call it a unit or unit of source code or module. So let's say a unit of source code, and it's intended to output a certain it's intended to be given a certain output. And in the case if the actual output matches the expected output, in this case we know that this particular unit of code works properly, otherwise it contains an error inside, right? So in case of the project I'm currently working on, the unit is the implementation of a single instruction for 6502 processor simulator in a specific addressing mode. So let's say load data to the A register, so LDA, and the immediate data. So this is one unit. Then load data to A register in zero page mode. That's another unit. And every unit might have either one test case or several test cases. Well, in our case, we'll have several test cases for every unit because of the nature of those units. This is going to be described a little bit later on. Okay, so now to next important thing. So advantages and limitations and disadvantages. So let me start with limitations and disadvantages, because that's something that I was clearly understanding back in the day. So testing will not catch every error in the program. So this was one of the main reasons why I didn't consider the unit testing, because it cannot evaluate every execution path in any but most trivial programs. So the idea is that in the real world it's not going to be working that nicely as in the test cases, because test cases are something that doesn't exist in the real world. And if we just test a single unit without outside of the context of the entire program flow, doesn't matter that it works properly, because the most issues might be arising in this entire program flow. And that's the case for business business applications I've been working on, because again, like having a single unit working properly didn't literally mean anything, because only the entire program flow did matter, because only that case I could have kind of make sure if everything is working properly or not. So the problem is a superset of the Houghton problem, which is undecidable. And the same is true for testing. Additionally, unit testing by definition only tests the functionality of units themselves, what I've just said. Therefore, it will not catch integration errors or broader system level errors, such as functions performed across multiple units, or non-functional test errors such as performance. So like the same what I just said, but in a bit more pretty way. Okay, and I've never been looking at the advantages, because these disadvantages were practical enough for me to reject unit tests once and forever. However, when we're writing in assembly language, it stops being that trivial as if we're writing in C or in Python or in JavaScript. So in assembly, instead of implementing the logic on its own, the logic of what the program is supposed to be doing, there are lots of things where you can make a bug, like produce a bug, make a mistake, in terms of how this works from the mechanisms of the assembly language on its own, right? So the goal of unit testing is to isolate each part of the program and show the individual parts are correct. So this is the exact thing that we're supposed to be doing here in this video. So separating these modules that do execute a single given instruction of 6502 machine codes and changing the internal state of this virtual CPU. So, and we exactly want to show the individual parts are correct. So individual parts in our case are a certain instruction within a given addressing mode, within a given showcasing how it works in the particular test cases. Okay, because even within the single addressing mode and the single instruction within the single addressing mode, but in a various test cases might potentially be given the errors. And before I found the bug from the previous video, where I've been just what I've been doing the previous video, I've been just loading some values to, yeah, it's not my project, it's just a project I'm calibrating my project by. So this is the JavaScript 6502 simulator, adopted by Nick Morgan and written by a guy back in the day many years ago, but it doesn't matter now. So let's say we have the following scenario, and like this, and then let's say LDA, and let's say 55, for instance. So if I assemble and enable the debugger, so first I load the value of 10, negative flag is not affected, 0 flag is not affected, but then we see like the 0 flag is affected because I'm loading the 0 value. And then the next step, the 0 flag is no longer affected. While in my code this wasn't the case, because once the 0 flag or negative flag has been affected, it was kept in that state. I didn't reset these flags. I didn't know that I need to do that, basically. And when I realized that, I needed to rewrite the test to verify whether a new updated code for LDA in the immediate mode is working properly. So I need to rewrite the entire test code for that, and that gave me an idea that every time when in future I would be realizing that I missed something, or in case if I would be altering the code to refactor it a little bit from the size perspective or anything, or just, I don't know, if I just want to be changing something within the code, I need to make 100% sure that whatever was working before these changes is still on the cards and it's still working, right? So in order to make sure that it is still working, I need to keep the test cases for every possible case, right? And this is exactly what the unit tests are all about. So this is exactly the case where this little unit of code allowing to execute these instructions, well, not in assembly, but obviously in machine codes, which you will now see how it works in my code. So in this case, it's really handy to have this sort of this kind of like test cases for every single unit. So the unit, again, like the unit is the LDA instruction being executed in the immediate addressing mode, and we have the cases. So the cases when we are not, when we're just changing the value of the register. So here it just prints the last one. The next case when we have the next case is when we want to set the value of 0 to a register. In this case, the 0 flag would get affected. And there also would be the case if the seventh bit, like the most significant bit, is set to 1. In that case, the negative flag is going to be changed from 0 to 1, right? So that should be handled as well. And if we just switch back from these, from the state where the flags are already being set to, like let's say this 55, where neither 0 nor negative flags are set, we need to make sure that both 0 and negative flags would get reset in case if they were set in the previous, after executing the previous operation or whatever. So this is very important, right? This is very important to know that we need to make 100% sure that these flags would actually, so not only the values are getting properly stored, but also the flags are handled respectively. So you see, like a single instruction, a single unit, but already 3 or 4 test cases, so depending on how you count, basically. By the way, initially I was going to make 4 cases, but I think now I will reduce the number to 3, because again, the amount of cases is going to be astronomical otherwise. So yeah, sorry guys. So yeah, just hold on a sec. Now let's get to the code that I have here. Oh my god, I've been showcasing this code in its previous states many times in the previous videos within this series on development progress on 6502 processor simulator. So just to point your attention to the very gist what I have here. So I have this execute function which takes the 6502 program as an input, and then it just executes it, and depending on what kind of source of what kind of opcode it encounters. So let's say here it encounters the LD immediate, the opcode for load data to a register in the immediate addressing mode, and here load data to a register from the 0 page. So this is known as the 0 page addressing mode. And every instruction has the specific opcode which are encoded in this instruction LD immediate, instruction LD 0 page. So these are the constants that has been defined in the very top of the code. So here is the A9 for immediate mode for LDA, and A9 for immediate mode, and A5 for zero page mode. But again, like, I didn't yet even finish doing with all the test cases in the immediate mode. So from now on in this video, we're going to be handling all the test cases in the immediate mode. So I will try to show how am I doing this. Like a bit of a live code in here would have been involved, right? So just to give you an idea how the process works. Well, obviously, one thing that I can say for sure about this, the way how I do this basically, is there would be really lots of duplications for testing code, which is not good. So this forced me to put to load the CPU simulator after the simulator random access memory. So I have around 600 kilobytes of memory there. So just to make sure that that would be enough for this binary executable, right? And anyway, if I just for some reason if I ran out of memory, I would later on would be able just to command out the tests, and it would be fairly enough memory for the actual executes statements. And the units that we're supposed to be testing are here. So here is the code that loads the data to the immediate, handles the load immediate data to the A register, and here is the code to load data to the A register from the zero page, right? So you see, like a test case actually takes more code compared to the implementation of the instruction, which is not that great. But again, like if I would be kind of like optimizing the tests, then I will need to write the test to test the tests, and that's going to end up with a total disaster eventually. So I don't want that. So I would rather go for duplications of the testing code, and then if needed, I will just command that out, or potentially even remove that, or maybe just move this to another file. Well, it doesn't matter from the memory perspective, because it's all memory in 16-bit real mode for x86 architecture processors is kind of like a single place, so it doesn't really matter if I split the files or not. But anyway, so yeah, now let's have a look how the output for a single test works. Then I'll briefly walk through what happens within these test cases, and then we'll start altering. I want to alter this one a little bit, and also I want to do what? Yeah, I want to write a couple more test cases for this load for LDA immediate data. Okay, so here I have a script to bundle all together and run the code. So here is how the debugging information looks like. So first, the test case prints that we are in the territory of LDA instruction immediate addressing. And here the next chunks of data we have are, here is the hex dump for where the 6502 machine codes has been stored. So A924 stands for LDA immediate value of hexadecimal 24, all right? And this is the actual source code that we have here to print, right? So well, you might argue that probably I'm just printing too big hex dump, but this can be altered. So I have a function to print memory dump, and it takes SI as the starting point and DI as the I register holds the end with the end address of, so from which address and up to which address do we want to print the data. So this can be altered. I prefer having this in like so, right? And just for now, so I'm not sure how this should be done in the right way, but just for now I'm using this. So what E stands for? So E here is because that's the offset for the simulated random access memory, so it starts from address E000. So from the simulated memory address perspective, so I didn't yet prove where the program counter is here, where the program starts, and respectively where the program counter is pointing to, but this might be changed so I didn't really specify this for now. So here you can just think that, like, if you want to observe this code from the simulated RAM perspective, not from the real RAM perspective, but from the simulator, from 6502 simulated RAM perspective, you can just imagine that instead of E you have 0, and then that's going to be the relative offset. So starting at 600 hexadecimal, temporarily I have the place where the machine code instructions are being hard-coded to, all right? And then here, starting from address 0, literally, so it's where the 0 page started. So here's the very first byte for a 0 page, and from here and up to 256 bytes down below, that's the first memory page, and that's the 0 page, right? So again, like for specific tests, we probably might have even slightly different kind of like these. So we probably we don't need that lots of code. Well, for instance, I believe that we actually don't need to print the memory dump because the immediate addressing is not using that. Probably that's the first thing to alter. Okay, but anyway, and next we have we are printing the state of the registers after this instruction has been executed. So you see, like, it does what it should do. So 24 has been loaded as the immediate data. 24 has been loaded to the A register. The rest, the X and Y register, remains unchanged. PF stands for program flag, and just to decode this, you might think of this order of flags. So we have the negative, overflow, reserve flag, break flag, decimal, interrupt, 0, and carry flags. So here we have like 0, 0, 1, 0, and this reserve flag is always set to true for some reason. So it's just like the default value for program flags, and the rest of flags are set to 0, right? Well, even though the decimal flag is a bit questionable, because depending on the specific processor, it might be set to 1 or to 0. So that's why they often say that you need to clear the decimal flag before anything else. But that's a bit of, that goes a bit outside the scope of this video in particular. So we're gonna be dropping that. So in my particular environment, I have this 20 hexadecimal, which is the encoded value of 00100000, which represents the value of all the flags in one byte. Okay, then the stack pointer, this is the standard, this is the starting point for a stack pointer, and the program counter has increased by 2. So it started at 600s and it has increased by 2. So now it's 602. So, okay. I'm sorry guys, just by the time I've been explaining this, I've figured out that there is another test case that I need to think of. So let's say if I just assemble and run. Nope, hold on a sec. I've been looking at this several times already, but anyway, so let's say I execute the first instruction, and here, so before I click the step, it doesn't go here. Okay, step, and after the next step, okay, so the next, so it just makes one extra step, and in my case, my program doesn't do it. So so this should be treated as okay. All right, I'm sorry guys, I'm just double checking myself, because this thing needs to be very, very precise. And this OK means that the unit test for LZ immediate mode for this particular test case has been passed properly. And now let's have a look at the at this test case code. So we start by resetting the CPU, which puts all the registers into the default values. We reset the memory, which zeros all the 8 kilobytes of the simulated 6502 random access memory. This here we initialize, so I put the machine codes in the little endian order, by the way. So I'm putting the machine codes for my 6502 instruction LDA immediate, so this is a opcode for LDA, and this is the immediate data of 24 hexadecimal. So we put this to where the test program is, and test program is just a variable down below this file, so nothing special really. So here is just the test program, and I'm using this as the test case for my execute function. This would probably be changed later on, so yeah. So for now, this is literally enough. Oh no, hold on a sec. Yeah, actually it's no. So I just I'm sorry guys. Let's start from scratch. So first I need to initialize the test program, and then I point SI to this variable, and then I call the routine to load the program into the 600 hexadecimal offset from the 652 simulated memory perspective, right? And then so what is this? I already forgot this. So test. Oh, this is just these are just the strings. So this line prints this line prints 652 machine code. Okay. Okay, hold on a sec. I feel lost. Okay, what? So test, point aside to the test immediate. Oh no, hold on a sec. So yeah, this string prints this message, right? Then these two lines prints. Let me just make it always on top. These two lines print this string. The next, I mean this two. Then I point SI to where the program starts and ZI where I want to stop. Well, but actually here it would be fairly enough to have, let's say, just plus 0.8, so 8 bytes is enough. And by the way, the debugging functions I've written so far work the way that it won't print less than 8 bytes in the row, so just to bear that in mind as well. So now it should print the only single line, so let me just quickly alter that as well. I just don't want to have the data that I don't need. Okay, then probably I don't need to print the memory dump because this instruction doesn't rely on that at all. So print memory range for program. Yeah, and here the new line and the memory monitor. Yeah, I probably I just don't want this at all. I'll put this code somewhere. I will later be I would be reusing this later on. Yeah, and up to this one. So I just don't need this code here at the moment. So all the code that is not used so far, I just dump it above, right? So let's have a look. So now it shouldn't print the memory dump because in this test case we don't really need that. So we have only the code, that the instruction that has been loaded, all right, and then print the register state after. Okay, this is cool. So let's inspect the code further on. So printing, so print memory range for program prints this line, or it alternatively could have print a real hex dump, like many lines, but one is literally enough here. We could have even not specified the DI at all, but in this case, in some cases there could be the undefined behavior, so it's always better to specify that. And by the way, so the implementation of this print memory range, I'm not even sure. Yes, probably still in here. Print memory range. Yeah, print memory range is here, and it relies on the global procedure print memory, which we have here. Print memory, which takes SI to point to the stored memory address, while here SI still points to the stored memory address to serve as the first argument for this procedure, and then DI points to the end, to the address where we need to stop. Print memory range, and yeah, and that's probably I just forgot to update. So print memory. Hold on, guys. I'm just wondering. I forgot where exactly. So see, like I I already don't remember how it works, even though I have every single line being commented here. Oh no, here it is, print memory range, yeah. And the DI, it compares with the DI in here in this. So yeah, so DI is specific to this print memory range, while SI is getting forwarded to procedures print memory. Okay, so this doesn't matter in regards to unit tested at all, but so just a very quick overview how the entire project works, but it doesn't matter really that much. So we did print the memory range. Then the most essential thing, we want to execute the instruction. And after we have executed the instruction, we want to print the state, the internal state of the CPU. And if this was, for instance, STA instruction to set a value somewhere to the memory, I would be forced to also print the memory dump for those values where I actually mean to put that value to. But as far as LDA doesn't involve that, we don't need the that hex monitor here, and it's just enough to print the register state. So here we have all the registers. So what are we in particular what are we interested in particular are the following things. So first test, now the unit tests, the unit tests on their own. So the first test is we need to make sure that the value at the A register is 24, and where this 24 comes from. So we load 24 to register A. So A9 means that we're loading to the register A, and 24 is the value, which means that by the end of this operation, we suppose that register A should be containing the value of 24. Hence this test case, this particular test case. And now, if it is so, then we move to the further instruction. If it's not, then we drop into the error. I will demonstrate how every single error in particular works, but let's first examine all the test cases. So the next test case is we need to make sure that the flags, no matter what the state of the negative and the 0 flag was before. By the way, this is not tested yet, so we'll add another. So we'll alter the value of the flags here to make use of this test, because for now it just tests with the initial value and we didn't do much. Well, actually, execute LD actually clears the flags, and if we have a look at the code, it actually clears the 0 flag and clears the negative flag. So at some point this is on the cards, but not really. So we need to make sure that we need just to shuffle the flags, then let's say just set both the negative and the 0 flag before running this instruction, to make sure that after we execute the instruction, the 0 flag would get reset, and as well as the negative flag. All right. So then the stack pointer. So stack pointer is not getting affected, but anyway, just to make sure that it's kind of still didn't change really. So well, I don't know. Probably this is a little bit of a redundancy. Probably we don't really need to check. Well, probably yeah, because we are not doing anything to this flag, then probably we don't even need this to be handled here. So just get rid of this. And then the program counter. So we need to make sure that after we have executed these two instructions, so initially it points here. So we need to add 2, so then the next step it would be pointing here. So the next operation, it's intended to look here. And oh my god, when I'm starting thinking about the so 0, 1, 2. Yeah, I just can't wrap my mind around everything for now, and that's another reason why to use this unit test. So I still have some questions about the program counter, because I don't yet have a proper test to test whether the program counter is working properly or not. So that's another like bit of an issue apparently. So well, maybe, by the way, maybe this is happening because in the execute function I'm not relying on program flag. So actually I'm not involving the program. So program flag is now just it's not used at any point, while in the real processor it's just everything is based on it because it points to the next instruction to execute. So yeah, it's a bit unclear for me how to deal with this. So again, like just to give you an idea that I don't know everything, and at this point, I just need to make sure that I did add this the value of bytes that we've processed to the program counter, and for now this is just enough. Okay. And if everything, so after all the tasks has been completed, it prints all done, and if it gets to this point, that means that the task has been passed properly. Now let's play around with the situations where, let's say, just to give you an idea, so it doesn't make sense, but if I compare with a different value, just want to show you how the errors is going to look like. So for instance, the value, the run value has been loaded to the A register. For some reason, let's assume that. So in this case, it would say the register failed, which tells me that there is something wrong with how the register, like how the data has been uploaded. Well, in this case, it's not wrong because it just I faked the test case, but I hope you see. So in case if here would it be like 24 and here not 24 but something else, in this case it would tell me that look here, so it doesn't load the proper data, and then I'll see, okay, so it doesn't load the proper data. I will know where exactly to look for an issue. Okay, so I hope that's clear. So now let me restore this back and save and run. Yeah, so now it's okay again. And then let's say something has gone horribly wrong with the flags, right? Well, actually, I can show you like this. So now say like flags fail because the flags should be a different value, but in this case, actually, they should look exactly like this, and yeah, only in this particular case. So yeah, as far as this was the real world bug that I've produced yesterday or today, I just want to show you this the following way. So another thing, so a part of moving the initializing the test program, I also want to set the registers. So I can say move byte to register P. In my case, these are the processor flags, and the value of, so let's say I want to set, so 1, 2, so this is the initial value. So here we have the negative flag, and here we have the 0 flag. So turn this to hexadecimal, this would be A2. Yeah, so let's put the hexadecimal A2. So let's say this was, so here I just want set 0 and negative flags to true. Okay, so this is just for testing purposes, right? And if I did everything properly, it should reset them and get this value back. All right, so let's have a look. Okay, all done, and we have reset this. And by the way, well, in this case in particular, it might make sense to actually print the initial debug info here. So I think if I just copy this, so here print the registers. Okay. Yeah, it just prints, but it's not the right place for it. So where is the right place? Test program, print memory range. Yeah, I think here is the place. And just to give an idea what is this all about, so let's say yeah, so you see that this was the initial value of the flags, and here we have reset flags, but I just think if I need to give some, well, probably I can say like CPU before execution and CPU after execution. So let's create CPU before execution and define by this is just the debugging string, so CPU before execution and new line carriage return well, let's say I don't have enough space, so let's say before execution, and it's clear that it's about the CPU, and copy, and here we'll have the after execution, right? So CPU after execution, and now I can print this strings as well. So it's not going to be needed in all the test cases, but just in this one in particular. So yeah, I think it's better as far as I have. I don't optimize the test cases. I'm free to alter them, so to be more specific. All right. So where is the print debug info? So here, I want to move SI CPU before execution, and I want to point SI to CPU before execution string, right, and call procedures print string. So here I'm using the global procedure print string that is available from everywhere. So print CPU before execution. All right, and now copy. So here I want to print it after, so paste CPU after execution points to CPU after execution, yeah. So let's have a look. So before execution, okay, so it's a bit wrong, so we need to have the new line character in the carriage return just right before. So this should be 1013 here. All right, and 1013 like this. Okay, yeah, now we have before execution, so the state before execution, and after, so registers or whatever after execution. So before execution we have this A2, that's the map for the flags. So we have the negative flags being set, the leftmost bit, the most significant bit, and the 0 flag is also set, hence this 2. So we reset this negative, the 0 flag, and so it's now 0, so it's 0, 0, 0, 0. And here we reset, so it's no longer A but 2, so only this reserved one, so 0, 0, 1, 0. So I just imagined the zeros and ones here because I didn't want to get bothered by actually implementing printing the binary strings here as well, just in order to avoid producing unnecessary bugs. Okay, so and now just to give you an idea how, so this wasn't the case. So now it's now this it passes this test case, but it wasn't like this before. So before I have implemented this procedures to clear the 0 flag and clear the negative flag. So before this was done, if I just run this, you see like flags failed because it didn't update the flags. So this what I would have in case if I didn't yet implement those routines to clear the flags. So as far as the value is not 0, so we need to make sure to reset the 0 flag, and as far as the value is not negative, so it doesn't have the most significant bit being equal to 1, so it's not F, E, A, or 8. I guess that's all the cases for where the most significant bit is set, right? So I need to reset negative and the 0 flags. All right, so here if I forget to do this, if I will forget to do this, I'll get an error. But if I restore it back, in this case, everything is fine, and I have this test case being passed properly. So I have all done, right? So and we've just completed the very first test case. Okay, now yeah, and by the way, by this time I already don't even need to manually reset the flags because they has been adjusted by the program itself. So now let's try to draft a couple more test cases for load immediate data. And here I need to think if I can just grab this code and copy paste it. So it's gonna be all the same apart from what? Apart from yeah, apart from I don't need to set the flags on start. So it's just copy, and here I want to paste, and save. Here I want to jump to test 3, which is going to be the next test case. So test 003, but it's just an empty label, so for now it just would drop to test completed. Alright, so I don't want to do anything with the registers, right? So initially, so before the B4 state should be 20 hexadecimal, right? And after, so in here, let me just see what kind of, so LD immediate, yeah, I would be using this one. No, it's the 0 page one. No, I want, was it already? Kick that away. Did I really? Oh no, I didn't. Here it is. Here it is. So this is the test case. Cut. And here. So now the program I'm loading is going to be this one. So A9 is still load immediate data to A register, but this time the value is going to be 00, right? And here in the commentaries, I just say what this code is actually what this machine code stands for from the 6502 assembly language perspective, right? Okay, so once I get this, so this print stuff is the same, right? And now I need to make sure about what the values should be. So, well, I can let me just command the test cases out. And I just want to see the layout to make sure it's exactly what I was looking for. And yeah, by the way, yeah, so it scrolls up the previous one, and I've also realized that for this, what am I, like, the kind of test class, I would say, I need to add a new line above. So where is that? Where is that? LD immediate. So if I say 10, 13, no, it doesn't fit here. So I just add I just put it here. So defined by 10, 13. And then this, and then yeah, so it's just the debugging string. Or probably I probably can put the separators. Yeah, let's say I can put a separator here. Oh, what have I done? Right, so put a separator here, new line here, instruction error, right, all done. Okay, machine code, memory monitor, and this. So you see, like, now it's more clear of what the byte to regard to what specific label. Test passed. So those that do end with a 0, I just separate them. Those that are multi-lined, I just let them be like that. All right, so here. It might seem that it doesn't make sense, but trust me, it does, because you're just getting lost in your own code quite pretty quickly if not doing so. All right, so what else? So yeah, immediate addressing. So now it should be printing immediate addressing like this. Well, and probably we can even yeah, just to make it a bit more visible, probably can do like so. So here I just want to define the byte, just want to print something like this, and debugging strain. Oh, oops, sorry. Something like this. Oh my god, what have I done? Oh, that's because I forgot to put a new line after. So can I just try to put it here? 13. No, it just doesn't fit. Fortunately, it doesn't fit, so it's okay. So define byte 10, 13. Define byte 10, 13, and debugging strain. Oh my god, what have I done? Run shell. Yeah, now it's much better. So you see, like, it's like visually separated now. So we have this LD immediate addressing, and yeah, and by the way, just want to have a look. If I just say stop, if I just stop here, then how it's still, yeah, so immediate addressing, yeah, so it's clear that everything goes below regards to this test case. All right, so yeah, now let's have a look at two cases. Okay, so but we didn't actually yet provide the tests. So the first thing I want to do, I need to manually test whether this code works properly or not. And what confuses me at start is why the heck does it load the 24 here? Well, it actually should load the 0. So this is the very first question I have. Okay, so oh, hold on a sec. Oh, I just put this. Oh my god, what have I done? So this should be 24, and these were the test cases for the very first one. And here I want to have 0, 0. Now we just starts giving errors, but it was okay for the previous one. Okay, so you see, like, yeah, I need to check everything very, very carefully. So let's here I just stop the execution again. So 24, does update the flags and does update the program counter, which is okay, and the tests are on, so these values should be okay as well. Now let's move to the second part. So now it should be trying to load the value of 0 to the register, and the previous value should be 24, and yeah, and it's not 24 because I did reset everything, and this is not good. So let's not reset the CPU, and I believe we cannot reset the memory. At this particular case, we don't need to reset the memory really. So we don't really need to do that. And probably, hold on a second, guys. I can probably, let's just say unit tests, and here I just say unit tests, and here I will already have the test 001 and like this. So I just want to put this reset CPU and reset memory outside of the scope, because I would be doing this from time to time if we need it, but not in this case. So let's have a look again. Okay, so immediate addressing, yeah, great. So now I have the register state from the previous instruction. So I still have 24 here. I have the same state for the flags. So initially it was A2, then it just got updated, it's still here. And now bear in mind the fact that 00, so this is the byte that we're loading to A register, but this is the 0, the value of 0, and this means that it should set the 0 flag to true. 0 flag is here, so it's 00100010, or 22 in hexadecimal, and we have this 22 in hexadecimal. So this means that it is okay. So the first thing to do, so the first test we can add here, and just to make sure that this test is correct, is the value at the A register should be equal to 0 after the tests, and otherwise it should fail. And let me just get rid of this stuff as well. Save. Oh my god, hold on a sec, but was it actually? Oh, it just said register failed. Yeah, I just didn't even notice that. Well, it said register failed, so let's just get rid of this, guys. Yeah, it now says the register is failed because it compares with 24, which is the previous value, but now this should be 00, and now still 0. Oh my god, why do you still fail it? Register failed. You must be kidding, man. Compare the byte. Oh, this is test 1. Oh my god, what am I doing all of the time? Yeah, you see, like it's really getting. I should have. Oh my god, guys, you see like how many chances to make horrible mistakes. So so I didn't. So starting from scratch again. So again, like trying to figure out the first test case, which is okay, which is cool. So okay, 24, and the registers has been set. Okay, and now so resetting this, guys, program counter. Okay, so now test 2. Okay, I'm in the test 2 territory, so comment now this, and now should be passed, but we're not checking anything, right? So let's start the checks. So the very first thing, so if I still compare with the previous value, it gives an error, right? But here it should be 00. So now it should be okay. and it is, and the value is really 0, 0, which gets into the register A, which is correct. All right. Then what? Then the flags. So if I leave the flags unchanged, it says flags failed, but we need to bear in mind that this should be actually 22, because this is correct, because the 0 flag has been set, so it should be 22 here. So here I just make this being equal to 22. So for this particular instruction, bearing in mind, this flag should be well, actually, it won't be 22 in case, if, let's say, the overflow flag has been set or a decimal flag has been set. In that case, it won't be like this. But from the context of the previous operations, we know that there was no things like that. Hence, this is the exact value. So probably it's not the best ever way to hard code these values like this, like how I do here. But this should be fairly enough, really. So, all right. So now flags are getting passed, so 22, and it should be 22. And now the program counter, well, program counter has not changed. Well, and this is another question, by the way. Yeah, so program counter, well, actually it says like the program counter has failed, because it has already executed 2 instructions, but as far as we didn't reset, as far as we did not reset the CPU, so I've removed those lines to reset the CPU. It doesn't reset basically, right? So I'm thinking, well, it is actually correct. It just won't happen in the real world that instructions would be replaced. Actually, they would be kind of like following one after another. I could have mimicked this as well, but I think this might be a source for some extra errors. So I don't know. I should either reset this by hands. Well, I would rather just say 604 instead, because this didn't change much, and it's still the 2-byte instruction. So we don't care about the absolute value. We care about the relative value as compared to the previous one. So it just added 2 bytes because the instruction contains 2 bytes. So it has increased by 2, which is correct. So I think this is just okay. All right. So now we get the value. We put the value to the register. It's okay. The program counter increased by 2. Stack pointer didn't change. The program flags are like so. All right. So it seems to be fine. Everything seems to be fine. And now we'll provide the very last test case for where we're going to be setting up the negative flag. All right. And then we'll end this video here at this point, and I'm going to be struggling with implementing the test cases for 0-page addressing mode, but I think you already got the point. So 3 test cases here. Okay, so what else? Now I just want to grab this test and put it here. So jump to test 4. Save. Okay, sorry, I've just been distracted for a while. So test 4. Okay. Here is going to be test 004. All right, and here, get rid of the test cases for now. And now I need to think. So first of all, that would have been another opcode. Yeah, let's say this one, say E, or it might be, so whatever byte, just to give you an idea. So this, for instance, E5, right? So this is going to be 1110 0101. So this is E5, right? This is going to be 85. This is what would be A5. This is going to be F5. But what's the similar thing about all of this numbers? That this byte is set to true, and if it is so, this means that the negative flag should get set appropriately, right? So, well, this is okay. So this is okay, and immediate E5, yeah, and just get rid of this. Test number 3. Okay, so the flags should remain from the previous instruction, right? So, well, let's have a look at the output. So what we have here, well, it says okay because it didn't test anything yet, but let's have a look manually. So A9 to A9, so let me just data E5. Okay, so the previous state, it was 0 because we did load 0, right? Yeah, we did load 0. Now we want to load E5 to register A. So this is correct. Okay. Then the flag, yeah, it's no longer a 0 flag, so it resets. So it's no longer 2 but 0 because it's just like 0 0 0 0. So no bit here with the 0 flag. So it did reset the 0 flag. The reserve flag is still still on the cards. It's always on the cards, but it also sets this flag for a -1, and now it turns to A. So this is correct. So E5, A0, and 606 for the point for the program counter. So let's put these values in. As far as they seem to be quite okay. So now it gets an error because that's the previous data which is run. Okay, register failed. But once we put E5 here, E5, and run, it now goes perfectly well. Then here we should, now it would be flag error, but I need to say to A0. Now I need to say to put it to A0, A0. And now it passes again, okay, and the program counter, it is something horribly wrong. What did I do? Exceeds the bounds. Oh, compare byte. Why compare? It should be compare word. Hold on a sec. But why did this? Hold on a sec. Yeah, it should be compare word everywhere. Okay. Oh, no. Hold on a sec. This was because, yeah, now I need to make it. Yeah, I just wanted to compare exactly the byte. I wanted to compare exactly the byte. Or in that case, no, hold on a sec. If I, no, that's still, I just compare with, I can compare like this, right? But this still might not be the case for the error. Oh, times -8. Okay, so I've exhausted the second segment. Okay, so the major reason is this one, because I've exhausted okay, so this can be handled quite easily. So I need to go to the boot sector, and for a simulator now I want to load 3 sectors. Okay, and for CPU down below I'm using 3 sectors. Okay, now works. Okay, program counter failed at this, please. This is interesting, so let's have a look. Why? Oh yeah, because this should be 6. Yeah, I was kind of like comparing this entire like 6 0 6, but this wasn't really actually only this byte was compared. So no matter if I type something here, it gets ignored. It just compares this part. So this would be on the cards as well, by the way. So see, like it says like it's okay. So yeah, just to avoid fooling ourselves, let's really compare with the byte, because otherwise it gets the warning that data exceeds the bounds, which we don't want to. So yeah, we really want to compare with this, actually with the byte, because if we exhaust this value, I will then be specifying the global value, like E60, like it would be E6FF, or no, it would be E7 already, E700 for instance. But it doesn't matter, it's just too far away at the moment. So let's check everything again. So LDA immediate addressing, so A9 E5. So E5 gets here, setting the negative flag. Alright, setting the negative flag, then program counter, and it's okay. So we got all the tests. Yeah, and here guys, here we have all of these just 3 tests. We have three test cases for a single instruction, load data to a register, to accumulator, in the immediate addressing mode. So the general case, we just resets the negative and the 0 flags. The case setting the setting the 0 flag when we load the value of 0, and the case setting the negative flag. So the case setting the 0 flag and the case setting the negative flag, because E5 has the most significant bit equals to 1, hence the negative flag gets affected because of that, and it should be altered. And here we see like that it does altered because A is 1010, so the most significant bit has been set to 1, which is the negative flag. So 10100000, and it resets the 0 flag from the previous instruction, because it's no longer a 0, because every time this immediate data call occurs, it actually resets. First thing it does, it resets the negative flag and the 0 flag, as can be seen here in load immediate data. Well, okay guys, this is from my side. I really hope that this video was useful in terms of how to think of unit testing in assembly language. And again, like I think that you see that in regards to this project in particular, this unit testing is absolutely essential thing to have. So if I was writing this, say, in C or in Python or in JavaScript, I wouldn't get bothered by this really. But as far as I'm writing in assembly, I really need to make sure that everything is under control. And you know, like, it really helps when you start like losing the focus of what you're doing. This unit testing helps you to unify everything, like put all the things together and make your consciousness crystal clear again, because you can control everything and you calm down and you have new power to proceed with the development. So before taking a decision to make this unit tests, I was like almost give up, because just I stopped when I had more than one instruction, not only this immediate but the 0 pages as well. I just stopped understanding anything, and I realized I really need some backup in a format of a test in order to make sure that I still control everything, and I can actually handle all the code that I've written so far. Okay guys, this is from my side. So yeah, thanks for watching. Until the next time, and take care.